All right, welcome back. We're going to do our best to see if we can finish off thermodynamics today. Maybe not, but we'll do our best. So the last piece of this is relating thermodynamics back to equilibrium. And that relationship is going to be captured by the relationship between K. Remember, K was the equilibrium constant. K stands for ratio of what to what? Products to reactants. So this is ratio of products to reactants at equilibrium. And then delta G naught, that's the Gibbs free energy change at standard conditions. And one thing I want to stress about standard conditions, there is one most important piece about standard conditions. And most people think it's the temperature or the pressure, but it's not. The most important thing about standard conditions, whenever we say standard conditions, we are talking about when all concentrations are 1 mole per liter. You can actually have delta G naught at different temperatures than 25 degrees Celsius, and we still call it delta G naught, as long as all the concentrations are still 1 mole per liter. Okay? So there's going to be a relationship between these two. First thing we're going to do is conceptually lay out the general framework of what that relationship should look like, and then I'll just give you the equation, which is on your formula sheet. But rather than just launch in and say, here's the equation, let's think about it for a moment. All right? So at standard conditions, Q equals 1. Remember, Q is the ratio of products to reactants at a given point in time. So at standard conditions, Q equals 1, because if all concentrations are 1 molar, it's 1 over 1. Delta G naught essentially tells us which direction the reaction wants to go. So recall, if delta G naught is positive, which direction does the reaction want to go? We repeated this on, I think, like 3 separate slides, so you can feel free to take a look back in the notes. If you can't answer that question immediately, take a look back, because this is very important. You want to have this at the front of your brain so that immediately you say, oh, delta G naught's positive. I know that means the reaction wants to go backwards. All right. So if delta G naught is greater than 0, the reaction wants to go backwards. From standard conditions. If the reaction wants to go backwards from standard conditions, then that means when it reaches equilibrium, if it's going backwards, it's making more what? Products or reactants? More reactants. So more reactants at equilibrium. And if there's more reactants at equilibrium, then that ratio, products over reactants, is going to be big or small? Small. So K will be less than 1. So the sign of delta G naught tells us if K is going to be less than 1 or greater than 1. So if delta G naught is negative, we can say all those same things in the other direction. Reaction wants to go forward. So we'll get more products. So K will be bigger than 1. So essentially, that's what these terms thermodynamically favorable and thermodynamically unfavorable means. Thermodynamically favorable means you want to make more products. So equilibrium will favor the products. It'll be a K value greater than 1. Delta G positive means it's unfavorable. That means it doesn't want to go forward, wants to go backward, more reactants at equilibrium. So you should understand that conceptually. And then there is a mathematical relationship. That mathematical relationship is delta G naught equals negative R T ln of K. This is on your formula sheet, so it's not something you need to memorize, but it is something you want to know is there and be able to apply when needed. All right, let's confirm that this equation matches our concept there. First of all, what if K is equal to 1? What if K is right in the middle? K equals 1. What's the logarithm of 1? The logarithm of 1 is 0. So if K equals 1, then delta G naught would equal 0. As K gets bigger, if K is bigger than 1, the natural log of a number bigger than 1 is going to be a positive number. So if K is bigger than 1, natural log of K is a positive number. So negative RT ln K would be a negative number. That's what we set up above. K is bigger than 1, delta G naught is negative. And if K is smaller than 1, natural log of a fraction is going to be a negative number. So negative RT ln K would be a positive number, which matches what we said about when delta G is positive. So first question was, is temperature always in Kelvin? Yes, definitely. You must always use temperature in Kelvin for pretty much everything except when temperature is changing, when you're measuring a delta T, because a change in the Kelvin scale and a change in the Celsius scale are the same. Something goes up by 10 Celsius, it goes up by 10 Kelvin. Change in temperature, you can use either one. But for any other purpose, you always need temperature in Kelvin. You can't have a negative temperature. Second question is, what is R? R is the same ideal gas constant. Oddly enough, we call it the ideal gas constant, but it's actually more universal than just for the ideal gas law, right? Because it shows up here in equilibrium, even for things that are in solution. So that's a good point. R here is the ideal gas constant. It turns out that constant that we call the ideal gas constant, that number was first come up with from dealing with gases. It turns out that number is actually more universal than just applying to the ideal gas law. It's more fundamental, and if you take statistical thermodynamics, you might get a better sense for the origin of that. But yeah, that R is that ideal gas constant. Now, if you look at your formula sheet, is there just one value of R listed? Take out your formula sheets. All right, so on your formula sheet, how many different values of R are listed? 3. All right, so let's figure out which one we should use. Delta G stands for what? What do we call this thing? Gibbs free energy. All right. So look at the 3 values of R. Which one has units of energy that we're used to seeing? The joules per mole Kelvin. We want to use 8.31 joules per mole Kelvin. right? Let units be your guide. You need to use the right units when you're applying this equation. One thing you're going to run into, Gibbs free energy is often given in kilojoules. R is in joules, so you're going to have to make those match when you want this equation to work. And then, yeah, let's point out explicitly here, temperature must be in Kelvin. Yeah, so we're getting into what we'll do a little bit today is some calculation. With calculations here, it's really just applying equations and making sure your units match. So for those of you, which is most of you with the bad habit of writing all your calculations without units, sorry. If you want to write your equations without units and just do everything incorrectly, that's your prerogative. It's a free country. But I expect you to write your units out. If you get something wrong on the test and you haven't included your units and I can't tell where you went wrong, your partial credit goes out the window. So just be in the habit of not being lazy, writing your units on all your numbers when you do your calculations, and you should be fine. Because all this is algebra. The one way you can mess it up is by not paying attention to the units. All right, so simple kind of question. Here's a reaction. Find the K value. Find the delta G naught value. Just conceptually, before you go ahead and do the calculation, when I look at this K value, the first thing I'm going to ask myself is this a big or a small K value? Is it bigger than 1 or smaller than 1? This is a small value. Since you have a small value, does that mean this is a favorable or unfavorable reaction? This is an unfavorable reaction. So then, when I calculate delta G naught, what kind of value should I expect for delta G naught? A positive value. So always do that kind of logical check. When you do a calculation, if you find that your value in the end that you get is negative, then you know you made a mistake in your calculation. Delta G naught in this case does not mean delta G of formation. Delta G of formation is a different thing. Delta G of formation is the delta G if you formed a certain compound from the elements it comes from in their standard states. Delta G here is the change in Gibbs free energy for this reaction. So the question is, why do we use the naught here? Why do we use this? This just implies at standard conditions. So we saw yesterday 2 different ways you can find a delta G naught value. One was using delta H naught minus T delta S naught. One was using the Gibbs free energy of formation values. So this is really a third way. So we're going to do a summary basically after this where we list those 3 methods again. But this one, you don't need Gibbs free energy of formation. You're given a K value and you have this equation here. So take 2 minutes and just do the calculation. Given this K value, find delta G naught. Okay, so I wrote the setup on the board. The main places you could have made a mistake would be not using the right R value, but we already specified you should use this one. You had to convert to Kelvin. The units kind of guide you here. So the units of bar are joules per mole Kelvin. You multiply that by Kelvin. The Kelvins cancel out. We're going to get an answer in joules per mole. And that answer is 37,700, something like that. Okay, 37,000 joules per mole. And that's a positive number, just like we said it should be. All right, so that's about as simple as a calculation can be. Just take the equation, plug in the values, watch the units. Now, as you change the temperature of a reaction, the delta G naught value will actually change. Remember that delta G naught equals delta H naught minus T delta S naught. And these two values here, delta H and delta S, these don't change much with temperature. So we treat them as pretty much constant values. But because there's temperature explicitly included here, as you change the temperature, delta G naught will definitely change. So if we know delta H naught and delta S naught for a reaction, we can find out what delta G naught will be at any given temperature. And then we can find out what the K value will be at any given temperature. So one application of this whole thing is we can figure out if I increase the temperature from 25 degrees Celsius to such and such, what will the new K value be? If I decrease the temperature, what will the new K value be? All right. So, slightly more complicated problem where you're going to have to apply these equations a few times is on the next slide. So it says a hypothetical reaction has delta H and delta G values shown below. Calculate its K value at 25 degrees Celsius and its K value at 80 degrees Celsius. Key point is that delta G naught is not going to be the same at 80 degrees Celsius as it is 25. So you can't just use the delta G naught equals negative RT ln K twice. You gotta do a little more work for this one. So take some time and work that one out. Work with each other. In K at 25 degrees Celsius. This is the relatively straightforward part. You're just applying delta G naught equals negative RT ln K. I just moved the RT to the other side, so I got ln K equals delta G naught over negative RT. So if I plug in values there, this is negative 27. I'm going to change kilojoules to joules because R is in joules. So negative 27, oh, sorry, not negative 27, negative 18,000 joules per mole divided by negative 8.31 joules per mole Kelvin times 298 Kelvin. So what value do you get for that? So question was, why is it 18,000? Negative 18 kilojoules per mole. I want joules and kilojoules to be able to cancel. So this is positive 7.3. So then I have natural log of k equals 7.3. So k itself is going to have to equal e to the 7.3. That's the reverse of doing the natural log. So you have that button on your calculator. So e to the 7.3 was what, like 1,400 something? All right, 1,430. If you said 1,400, fine. Okay, so what questions do you have about that part? Finding k at 25 degrees Celsius.
I came out with 0.0076, but maybe I was supposed to multiply that by 100, and that would have gotten me 7.3. I don't know where.
Yeah, so if you came up with 0.0073 for a natural log of k, that's because you didn't change kilojoules into joules. Yep. Would be right. So here's the thing. Units are an important thing. NASA once lost like a $1 billion spacecraft because someone forgot to change foot-pounds into Newton meters. So there's... Units are an important thing. You can say, well, I was almost right. I was only off by a factor of 1,000. Yeah, okay. Next time your paycheck comes from your job, if it's off by a factor of 1,000, they give you 1,000th of what they were supposed to give you. I don't think you're going to say, oh, well, they were almost right. You kind of... Factor of 1,000 is important. All right. So other questions about finding k at 25 degrees Celsius? Now, if I want to find k at 80 degrees Celsius, I have a complication. I want to use this same equation, delta G naught equals negative RT ln k, and you might think, oh, well, all I need to do is plug in the new temperature. But what you're ignoring if you do that is the fact that delta G naught at 80 degrees Celsius is no longer the same value. I can't just use negative 18 kilojoules per mole for delta G naught at 80 degrees Celsius. It's not going to be the same value anymore. So, I saw a lot of you took a three-step approach. What did you do first? Use the equation delta G naught equals delta H naught minus T delta S naught to find delta S naught. Then once you have delta S naught, you can then use that same equation to find delta G naught at 80 degrees Celsius. And then the last thing you would do is now apply delta G naught equals negative RT ln k. To find that new k value. So it's a little more complicated. There's a few more steps. And it stems from the fact that you can't just use the same delta G naught value at 80 degrees Celsius as you did at 25. Yeah, so the question is this a general process? It's not necessarily a general process. It's the process based on the information we were given, right? Because we were given delta H naught and delta G naught, we needed to find delta S naught first. in a different scenario, we might have been given delta S naught first. So I can't say that, like, this is a general process you're going to always apply. Generally, what you want to do is think about where it is you want to get to. Where it is we wanted to get to was to be able to use delta G naught equals negative RTLN K to find K. That led us to the idea that, oh, delta G naught is an unknown there, so we're going to need to find delta G naught. So really, the thought process goes in reverse. I want to do step number 3 to find K. But because I don't know delta G naught, the step before that is going to have to be finding delta G naught. All right, in order to find delta G naught, I need delta H naught minus and S naught, delta S naught. I wasn't given delta S naught, so then I have to go back to step 1. Step 1 is going to be finding delta S naught. So really, the thought process goes in reverse order here. Think about where you want to get to, and then work your way back until you get back to the information you have. So in step 1, you're finding delta S naught at 25 degrees Celsius. But what we said is delta S naught and delta H naught are pretty much constant with temperature. So delta S naught and delta H naught at 25 degrees Celsius are going to be the same as delta H naught and delta S naught at 80 degrees Celsius. By saying they're constant with temperature, I mean that delta H naught and delta S naught are fixed values. So delta H naught at 0 degrees Celsius and delta H naught at 100 degrees Celsius are the same value. All right, so the question is, but didn't we, yesterday we were talking about the voices. We're talking about the voices of delta H naught and delta S naught, and whose voice got louder as T changes. Yeah, the voice of delta S gets louder as T changes because you're multiplying delta S by temperature. So as you multiply by a bigger number, the importance of delta S becomes more important. But the actual value of delta S stays the same. It's just you're multiplying it by a bigger factor as you increase the temperature. So when I said delta S's voice gets louder, basically that's because it's using a megaphone. It's not because it's actually speaking any more loudly. The value of delta S is still the same at each temperature. So delta S is a number, like 50. At 5 degrees Celsius, or say at 5 Kelvin, this term, T delta S naught, is 5 times 50. So 250. All right? At 10 Kelvin, this factor, this term, T delta S naught, is now 10 times 50, so 500. Even though delta S stays the same, and delta H stays the same. So delta H is a number, delta S is a number. They stay the same. As temperature changes, it just happens that the delta S term gets bigger and bigger and bigger because you're multiplying by temperature. Delta H does not get smaller. Delta H stays the same. Delta S is not bigger. T times delta S gets bigger as you increase the temperature. So yeah, let me see. Let me see if I can. All right. New slide. Give me a little space to write. Why won't you give me a new slide? There we go. All right, we have our two people. Delta H and delta S. All right. We have our two people, and they are both speaking. All right? They're both speaking. Now, yeah, so the shirts are a little big. I'm not a great artist. The funny thing is my daughter's like obsessed with Despicable Me right now. So what I'm picturing really is like two little minions like having a shouting contest. So they both speak in a certain voice. All right? Now, as you change the temperature, what happens is delta S uses a megaphone. Right? So how do I draw a megaphone? I want it to change color. All right. So it's using a megaphone, right? And as you increase temperature, the size of the megaphone gets bigger. So that megaphone is the temperature factor. Okay? So the size of their voices stays exactly the same. But as you increase the size of the megaphone, delta S gets louder and louder and louder, even though it's speaking at the same volume. Right? The value of delta H and delta S are fixed. They are fixed numbers, 5 and 10, or 212. Whatever they are, they're fixed numbers. T is like a megaphone that is amplifying that S number because you multiply by T. Right, so let's just put in numbers. Let's say delta H equals 5,000 joules per mole, and delta S equals 200 joules per mole Kelvin. All right? Let's make them both negative. Oops. Just to put in those numbers, okay? If T is 10 Kelvin, delta G would equal 5,000 minus 10 Kelvin times 200 joules per mole Kelvin. So 5,000 minus 2,000 would be positive 3,000 joules per mole. All right? If, on the other hand, T equals 100 Kelvin, then delta G would equal 5,000 joules per mole minus 100 Kelvin times 200 joules per mole Kelvin. So now that's 5,000 minus 20,000. Now it's negative 15,000 joules per mole. Delta H and delta S have stayed the same, but temperature got bigger, so delta S's voice got louder. Oh, sorry. Oop, I forgot my negative sign there. Oops. Yeah, we'll have them both be positive. All right. That is why delta G depends on temperature, even though delta H and delta S do not. All right. No, don't be sorry. This is why I do this in a room full of students instead of doing it in a room by myself. I need your questions because someone else will have the same question when they're sitting at home watching. And they need the diversion of being able to draw the little stick figures. All right. So from there, and the concepts here are much more important than the actual calculations. Now you would apply this three-step process, okay? That three-step process would be finding delta S naught, using delta S naught to find delta G naught, using delta G naught to find K. And you know what I'm going to do? I'll say, I will post the mathematical solution from A block, because we did this in A block. And it's just tedious chugging through the numbers doing algebra at this point. What we found is that K at 80 degrees Celsius, when we went through that process, K was like 260. All right. So K is 260. It was 1430. We get 260 as our answer at 80 degrees Celsius. Always we want to ask ourselves, does that make sense? Okay? So we have this reaction. Delta H naught is negative 27. Is this endothermic or exothermic? This is exothermic. This tells me that it's exothermic. All right. Since it's exothermic, I know that I have reactants turning into products and also producing heat. So if I raise temperature, essentially that's the same thing as adding heat. What does Le Chatelier have to tell us about adding heat to this reaction? All right, reaction should shift to the left. And if the reaction shifts to the left, I should get more reactants, fewer products. And if I have more reactants and fewer products, K, which is products over reactants, K should go in what direction? K should go down. All right. Let's confirm. Do our calculations match our conceptual understanding? K had been 1430. It's now at a higher temperature. It's 260. K went down. So, check. All right, what questions do you have about that process? Good. Let's, there is, essentially what we were doing there was applying our two equations. We know that delta G naught equals delta H naught minus T delta S naught. We also know that delta G naught equals negative RT ln K. So sometimes it's going to benefit us to put those two together and know that delta H naught minus T delta S naught equals negative RT ln K. And we can use that to find the relationship between T and K. I could do a mathematical derivation and come up with an equation relating temperature to K, but I'm going to skip that for right now. So the question is, can I go over the relationship between delta G naught with that standard conditions and delta G, non-standard conditions? I can, And I will tomorrow. You can see I have several slides devoted to it. So we will be doing that tomorrow. I did it in A block, so if you look at the A block notes tonight, you can see what we did there. So the question is, can you cancel out the t's from both sides in this equation? Well, not entirely, right? Because on the left-hand side, there's only t in one of the factors, in one of the terms. So what I can do is I can divide both sides by negative RT, but t is only going to cancel in one of the terms on the left and not both of them. And so, you get a relationship where temperature is still in it. It's not canceled. And that tells you, as t changes, K is going to change. All right, let's just close with a summary because we've talked about 3 things that are equal to delta G naught now. One we talked about last time, the other 2 we've used today. So if you have delta G of formation values, if you're given a table, you're allowed to look in the back of the book, then you can use delta G naught for the reaction is going to be equal to the sum of delta G of formation for the products minus the sum of delta G of formation for the reactants. So that's one way to find delta G naught for reaction. A second way is if you know delta H naught and delta S naught, then you can use delta G naught equals delta H naught minus T delta S naught. And a third way would be if you know the equilibrium constant, we now know that delta G naught equals negative RT ln K. So on the problem set, for the there's a lot of conceptual questions on the problem set. Those are the most important ones. Then there's some calculation questions. Those calculation questions are really about using these different equations. So taking the given information in a question and figuring out, okay, given what I have, which equation can I now apply? And you kind of mixing and matching and using the right equations. Less important part of the problem set, not our main point of emphasis, but it's there. So we have these equations you're going to use a lot. Good news is they're all on your formula sheet, so you do not need to memorize any of them. And tomorrow we'll talk about how these standard conditions relate to non-standard conditions. All right.